Hello, and welcome to the Freeway Segment Safety Performance Function Development webinar. My name is Paula Hyman from the Ohio LTAP Center, and I'm going to be your technical support for today's webinar. Before we begin, if you have questions throughout this presentation, please type them into the questions box. Our presenters will address your questions at the end of the presentation. If you could go ahead and locate that questions box, go ahead and type just the hello, hi to make sure you know where it's located and how it works. Lastly, there is a copy of today's presentation available to download in the handout section. If for some reason you are unable to download the handouts, they will be emailed at the completion of the webinar to the group. The webinar is also being recorded. Providing that the recording is successful, the YouTube link will be emailed to all participants and uploaded to the LTAP website. I want to thank you in advance for your participation. And with that, I'm going to pass things off to Mr. Scott Himes with VHB. Scott?
Thank you very much. Welcome everyone to the webinar today, talking about the Freeway Segment Safety Performance Functions that we developed for Ohio. I just wanted to give introductions really quickly. My name is Scott Himes. I'm with VHB in Raleigh, North Carolina. I'm a highway safety engineer that focuses mainly on highway safety manual implementation and development of SPFs and effectiveness of countermeasure installations. Ian, would you like to go ahead and introduce yourself?
Sure. Hi, everyone. I'm Ian Hamilton, also a transportation planner with VHB here in our Raleigh office. And I sort of specialize in safety planning and data management and analysis.
Thank you. Kendra, would you like to introduce yourself?
Sure, yes. My name is Kendra Shank. I work with Burgess & Nyepel here in Columbus, Ohio, and was a subconsultant to VHB to develop these freeway segment SPFs. So do a lot of work in Ohio with the safety program there.
Thank you. And before we get started, I just wanted to give a special shout out and thank you to Mr. Derek Troyer from the Ohio DOT, as well as our technical panel for their oversight on this and great feedback that we received as we were moving through this effort. So thank you to everyone involved. So the agenda for this webinar, I'm going to provide just the introduction, motivation, and objectives for the work that was completed. Then Ian will talk about the data collection and integration effort focused mainly on the project design level safe SPFs that we developed. And then I'll go through just a very high level overview of the two different types of SPFs that we have developed as part of this effort. And then Kendra will finish with talking about the project level validation that was completed, as well as the implications for design level analysis. And then at the end, as time allows, we'll take any questions and answer those. So just the introduction and overall objectives for this work. We recognize that SPFs play a critical role in reliable safety management. We sort of recognized over time that safety performance is directly related to traffic volume and as well as other potential features of the roadway. And it may not always just be a linear relationship between crash frequency and traffic volume. So we recognize that as volume increases, there's an interplay involved in how crash outcomes change along with that. So SPFs are very important for identifying how those relationships exist for different facility types. So with those, SPFs serve two primary functions. The first is network screening. So very high level SPFs are used to identify what the average crash frequency for a site would be using just traffic volume and segment length. And then from that, we can identify segments that are overrepresented with crashes. So the figure on the right here just shows an example of the top 5% of sites that are overrepresented with crashes, and then sort of the next 10% that we can then take into the roadway safety management process to identify what is going on in those segments, why are we seeing above average crash frequency, and is there anything we can do to help bring the crashes down on those particular segments. And then the second approach is for project level safety prediction. So with those SPFs, we get into more what factors from the roadway geometry, traffic operations, or other considerations are also involved in the safety performance. And we can really nail down what is the predicted crash frequency for a segment with all these characteristics to then get into some design level trade-off analyses. So if we decide to lengthen a speed change lane, for example, or add an additional through lane, what would be the overall impact to safety performance based on that? So there are basically two methods for obtaining SPFs. The first is to calibrate existing SPFs. This is pretty common. We have national SPFs that are found in the Highway Safety Manual, and those can be taken and calibrated to specific jurisdictions or circumstances. But what happens when you calibrate an SPF is the overall shape of the SPF is retained, and it just kind of shifts it up or down. When we see an example like shown on the screen here, where maybe the total crash frequency or fatal and injury crash frequency doesn't exactly mirror the relationship we're seeing on average overall for an entire range of ADT, it may even out, but within certain ranges of that ADT, the existing SPF may not perform particularly well. And so when we have a case like that, it may be better to develop an SPF from jurisdiction-specific data, which requires just a little bit more data collection than what would be used to calibrate an existing SPF. So the motivations for this project were that Ohio had first completed a calibration of the Highway Safety Manual's project design level models, and they prioritized those based on the site types that were predicting the poorest. And what they ended up finding was that there were some counterintuitive relationships that were found, particularly on freeway segments when adding lanes. In general, the idea is if we had the same traffic volume, if we would add a through lane in each direction, we would expect that the crash frequency would decrease. But in some of the cases, given those scenarios, we were seeing that as you added lanes, the predicted number of crashes actually went up. And I do want to just point out that as part of this research, we did actually confirm some of those findings, that we did have some of those counterintuitive relationships still existed within the data, even when we developed new SPFs from the ODOT specific data. But an additional goal for this and motivation for this was to have directional prediction models, particularly for the project design level. Right now, the Highway Safety Manual's design level analysis for freeway segments predicts crash frequency for both directions combined, and that can get into some issues when we have freeway sections that aren't exactly symmetrical, and we may be looking at just making changes in one direction. So the idea being, if we get into a directional prediction, we can get a better level of detail in the analysis that we're conducting. So the overall objectives for this work were to develop the planning level SPFs for ODOT freeways that can be used as part of the roadway safety management process. Then look at developing bidirectional and directional project design level SPFs that are consistent with those found in the Highway Safety Manual, and then evaluate those SPFs along with the HSM CMFs for performance. So it's kind of wordy there, but what we did as part of this effort is look at the base SPFs we developed as part of this research, along with the new CMFs that we developed, and compared those to the performance of the base SPFs from this research, along with the Highway Safety Manual CMFs, to see how well the predicted performance compared to each other. And then from this effort, we suggested updates to the ECAT to incorporate the recommended project design level SPFs. So with that, I'm going to turn it over to Ian to first talk about the data collection and integration.
Yeah, thank you, Scott. So letting my screen load here. So like Scott mentioned earlier, I will be presenting on the data collection integration effort specifically related to project level SPFs. And although we really did a fair amount of work sort of doing our own customized data collection and integration effort, I really hope that it shows through that a lot of hard work has gone into the data preparation prior to this specific effort. So a lot of hard work from ODOT staff, collecting data, integrating data for their own safety management program. And so when we sort of look through the examples here in the next few slides, I hope that sort of it comes through in the presentation. And I think really the best example of just the great data that we had to work with sort of shines through with the size of our study area. So as you can see in this figure on the right, we really did cover a really great proportion of the state in terms of freeways. And so collected data for several freeways, including interstates and state routes, and a really good diversity of regions, including topographical, going east to west, as well as a good cross section of urban and rural locations. And so again, if we really were starting from scratch here, we would not be able to achieve the comprehensiveness that we did with our study area. And so I just want to make sure that that's acknowledged. And so our approach consisted of a combination of manual and linear referencing techniques, some of which sort of help the groundwork, sort of developing some of these complex data sets, and then utilizing the linear referencing for some of the automation for later in the study. And so looking at the existing inventories, we were able to pull a lot of information from ODOT's existing comprehensive data set. So things like through lanes, median type and width, shoulder widths, and then of course traffic and ramp locations. And those really are sort of the bread and butter needs to develop safety performance functions. But we were able to access a lot of other supplementary data sets that really are sort of unique to the ODOT context. So things like barriers, both inside and outside, lighting inventories and interchanges, and curvature in some aspects. Again, these are not common elsewhere in the country. And so having this access to these data in such a comprehensive manner really sort of helped pave the way for an efficient data collection process. And as Scott mentioned, we collected data for both directional segments and bidirectional segments. And we'll sort of walk through some examples later. But again, being able to inventory all this, both bidirectionally and unidirectionally, really helped us out with our efforts. And so looking at what we did manually, we started off by locating ramps, specifically the ramp gore locations, as well as any sort of beginning and ends to tapers. And that then classified those locations according to whether or not they were a speed change lane or lane add, lane drop, classified whether they were a left side ramp or a right side exit. And then we were able to flag any recent construction. So as we sort of drove the corridor and dropped our points and identified our ramp locations, we were able to use Street View and historical imagery to identify any construction that might have occurred during the study period. So then we were able to buffer those out, and we'll talk through a little bit how we did that in a second. We were also able to exclude any sort of atypical locations. And so some examples including like toll plazas and rest areas, locations where they don't necessarily conform to the literature and the research and may sort of produce some counterintuitive results. And so by driving the corridor, by locating these ramp locations, I'm really able to sort of tease out some of these confounding areas. And although it isn't quite listed here, we were able to identify weaving segments by weave type. And I believe we'll cover that examples later in the presentation, but just want to make sure that that's acknowledged that the weaving sections were collected manually as well. And so that allowed us to produce 3 data sets, one for speed change lanes, and then one for directional segments and bidirectional segments. And again, really want to highlight that ODOT's LRS, really made the process of developing these data sets, integrating these data sets incredibly simple and straightforward, and really allowed us to focus on some of those tertiary data needs where, that really allow us to enrich the data sets and collect some of those information that aren't typically included in safety management programs. And the LRS really is helpful for locating those relative positions. So a lot of the data that we'll see is collected both upstream and downstream, and not just on the segment itself. And so being able to locate those relative positions is a great asset to this effort. And so Just sort of give a quick background on linear referencing and what it allowed us to do. I think one of the key things that, really made things simple was being able to, once we had identified those construction and atypical locations, being able to buffer and remove them from the data set. Were you to do that in sort of a simplistic spatial relationship, it would create error, it would create situations where you've got incorrect measurements, but being able to do that along the LRS really made it simple to remain consistent and develop clean data sets. It also really helped with locating those supplementary data sets I talked about. So those barriers, those curvature, that lighting, other information we wanted to collect. And really where that shines through is both the directional and then translating that information to the bidirectional. So, again, if you were trying to locate these features purely spatially in a directional manner, it could create error, it could create discrepancies, and then trying to translate it into a bidirectional fashion would be incredibly difficult. And again, would just create inconsistencies that we wouldn't want to see in the data set. And so having that strong LRS background really benefited this effort. And then, of course, like I mentioned, able to locate relevant ramps for certain segments, and especially locate those ramps upstream and downstream of our segments. And so certain information, whether that be entering traffic or exiting traffic or weave sections, being able to classify those at the segment level based on upstream and downstream information really made this effort pretty straightforward. And then just so it's clear to everyone, routes are already dynamically segmented based on ODOT's base data. And so that really is helpful because it allows us to create those uniform segments pretty easily with minimal data processing. And so again, by having those uniform segments at hand, readily at hand, we're able to focus on some of the more complex calculations, both upstream and downstream. That said, I do want to highlight one challenge that's associated with just the way that ODOT happens to store its LRS information. Some states do this and other states don't, but most information is sort of stored according to this county-based route system, where the mileposts break along county boundaries. And for the most part, except for very, very, very typical or technical reasons, there really is no difference between an end-to-end or a county-based mileposting system. But for the purpose of identifying upstream and downstream segments and keeping sort of the flow of the route in check, it did present some challenges. And so wanted to highlight that in order to overcome this, we basically reconstructed a temporary LRS to both calculate the upstream and downstream elements and keep our sort of weaves and ramp ADTs organized by segment. And this, of course, stayed faithful to the line work and stayed faithful to the distances in the line work, but it really sort of helped us sort of track the flow of traffic and the flow of data elements along the route. And so looking at what that looks like in practice, you can sort of see this one directional segment here where the directional segment is in purple. And then you can see those upstream elements in blue and those downstream elements in red. And so you can see how this westbound traffic in this directional segment, we're able to account for that downstream ramp exit highlighted in red and that upstream ramp entrance highlighted in blue. And again, just being able to relate those elements in space and keep our data in order and keep it within the flow of traffic really made this process very simple. And I think really yielded dividends later in the model development process. And so then just quickly highlighting the directional and bidirectional segment development, we chose to develop directional segments first because that allowed us to sort of get our ducks in a row and remove our speed change lane areas, as you can see in those gaps in the red line work, and then also buffer out those atypical situations. So again, removing those construction areas, removing those sort of toll plazas that aren't necessarily accounted for in the line work or in the model development. And then pretty intuitively, I think the directional segments just referred to a single cross section according to a single direction of travel. So the number of lanes, the shoulder widths associated with that single directional travel, and then any barriers or lighting that might be associated with that direction. And I think one important thing to note that may not be intuitive to the group or may not be clear in the report, if a segment did contain more than one weave, and through our manual effort at ramps, we did identify locations where there may have been more than one weave present, we always took the lower letter. So a C took precedent over B, and B took precedent over A. And so this will, both the weaving types and the sort of results in the model will be explained later. But I just want to make sure that that's clear up front. And so developing bidirectional segments really was pretty simple. Once the directional segments were already developed, being able to develop those segments based on overlapping directional areas. Once we had removed those construction segments, those speed change lanes, any atypical situations that may have been present, it really was just a matter of sort of folding those together and developing that full bidirectional cross section. And so if data needed to be aggregated across both directions of travel, we did so. The obvious example being, say, travel lanes or barrier coverage. But there are also common values. The most obvious example being speed limit. If those needed to be shared between both directions of travel, we did so. So that made things pretty simple. And again, because we'd already done the upstream and downstream detection based on the directional segments, it was a simple matter of sort of integrating that into our bidirectional segment development. And then if for whatever reason a directional segment had been truncated, so you weren't able to develop a full overlapping bidirectional segment, and it might have changed or offset some of the upstream and downstream distances, we recalculated that to make sure that we had both the right associated data as well as the right distance to that entrance and exit data. And then again, for weave sections, these same rules applied for bidirectional segments as they did for directional segments. And so with that overview in mind, I do want to hand it back to Scott to then cover the SPF development approach.
Great, thank you, Ian. So I'm going to give a very high level overview of both the network screening and the project design level SPFs. I think that just based on the sheer amount of work and number of inputs and outputs to the system, we could probably spend 2 hours just going through that by itself. So if you do have any more questions, please feel free to reach out. Also, the final report will be made available, so the details are all contained within that document. So just at the kind of higher level, talking about the network screening SPFs first, we focused with the highway safety manuals approach for network screening, looking at the SPFs being a function of only segment length and ADT. The impact of other factors is ignored. The more that you account for different features at this level, the more refined your predictions can be, but may give you less opportunity to identify things in diagnosis that are impacting safety and could be corrected. So we try to keep them pretty high level for screening the network for overrepresented sites. So the two model forms that we tested for network screening were the power model and what's called the HURL model. The power model is the typical model that you would see and is considered to be the base SPF in most cases, where we have segment length as an offset variable. So if a segment is twice as long as another one, you would expect exactly twice as many crashes to occur. And then we have log ADT included in the model, which is just rearranged in this format to say that it's ADT to the power of B. And then we included indicators in here for different districts within the state. So we used the Ohio districts to help refine some of the safety prediction to account for things like different driving populations, and you may have different weather patterns, different terrain, things like that, that may account for some of the safety differences, which is essentially similar to developing an SPF specific to the more localized jurisdictions within the state. But in this case, it does act as an offset for the prediction. So it just kind of moves that mean prediction up or down slightly if it's different across the districts from others. And then the HURL model just incorporates ADT in two different ways, including log ADT and then just ADT, that allows for some interaction as you change the traffic volume. We know that as volume goes up, it can have this differential impact on crash frequency as you get more interaction between vehicles. So this model form just gives you a little bit more flexibility to account for some of those differences. And so in this case, for network screening, it is done at a bi-directional level. So the models predict crash frequency for both directions of travel together. So just providing some overall numbers here. This gives us a breakdown of what we looked at in terms of the different SPFs that we created. We looked at rural and urban areas separately. In the rural areas, we had 4-lane and 6-lane segments. And then in urban areas, we classified them as 4-lane, 6-lane, or 8 or more. We did have a few cases where we had 5-lane and 7-lane sections, and we just folded those into the 6-lane and 8+ lane as we needed and what made sense with the data because we would add really small sample sizes there. And so then we did differentiate the SPFs, whether they were traditional base freeway segments, kind of free and clear of any influence of the interchanges. And then we separately developed the SPFs for interchange segments, and we defined the interchange segments consistently with what you would find in Safety Analyst, where in general, the interchange segments are defined as being the gore-to-gore location to the farthest extents of the interchange, plus or minus 0.3 of a mile. And because Ohio already uses Safety Analyst, again, we got really, really good data from the state on this. And so we already had the information on which segments were interchange segments and which ones were base segments. So we just used those existing data definitions for this. So in general, you can see that across the board, we had pretty good mileage for each of these categories, as well as really nice sample sizes for total crashes and fatal and injury crashes for developing the SPFs. In general, the kind of rule of thumb is you'd like to have at least 300 crashes per year per SPF site subtype to develop the SPFs. And you can see that for the rural interchange segments, we're the only ones that were pretty close on that. Everything else, we had very large sample sizes. Okay, so here's just an example representation of the final SPF. So you can see that with the Hurl model, we can get a little bit of flexibility built into the SPFs. So if you look at the blue dotted line, that is the total crashes SPF for base freeway segments. You can see there's almost a little bit of an S shape to the curve. That's the Hurl model giving you that little bit of built-in flexibility to predict the crash frequency. And then you can see that given the same volume, we have higher predicted total crashes for interchange segments given the same length and same volume. And then you can see the SPF plotted here for the base segments fatal and injury, as well as the interchange segments fatal and injury. And I believe this example is for rural 4-lane freeways. So how did we assess those? This was a pretty detailed process as well. I just wanted to highlight for the validation purposes, because we used all of the segment data to develop the SPFs, we used the cumulative residual plots as our main means of validation in this case. And so what the cumulative residual plot allows is it allows you to plot the difference between the predicted number of crashes and the observed number of crashes for each segment in the database, and then aggregate those along some value. So we could have plotted those against predicted crashes, or in this case, we plotted it against freeway ADT to look at where does our SPF perform well and where does it not perform well. So we have a lower 95th and upper 95th confidence interval that says as long as we're within that, we're predicting within the sort of range of random error. If we're outside of that, it means we do have a little bit of bias built into that SPF. And so what we would like to see ideally is our line to be along the 0 point, that we have no cumulative difference among any sites. But you can see where we have longer ranges of kind of sloping up or sloping down values, it means we have a little bit of bias in the predictions based on the individual sites. And you can see overall, this SPF did very well. It does oscillate about the 0 line. There's a little bit of issue between 32,000 and 42,000 ADT, but in general, it met our rule of thumb that we'd like to have fewer than 5% of sites exceeding the confidence interval, which we did in this case. So we used these cumulative residual plots to identify where they were not predicting well. If we had any outliers, we had huge jumps or huge decreases in the cumulative residuals, we could use that to identify outliers to potentially remove from the data set as necessary. So in terms of the project design level SPFs, we really tried to design this to follow along with the Part C predictive methodology that's in Chapter 18 of the Highway Safety Manual currently. So we took this to include additional features so that we could improve the predictions at the individual site level, and so that we can use those to evaluate the effects of the different changing features. But it was subject to the data that we had available. And as we talked about before, we did test looking at predicting both directions combined, as well as predictions based on the individual direction. Again, along the lines of the current edition of the HSM, we've developed separate SPFs based on crash types and crash severity. So for each of these, we ended up with 4 SPFs, multiple vehicle crashes for fatal and injury versus property damage only, and then single vehicle crashes that were fatal and injury versus property damage only. And then within the fatal and injury crashes, we did look at individual severity levels using severity distribution functions, which really just are used to identify what proportion of crashes are made up of individual severity levels, which can then be used as a multiplier to crash frequency to get at a number of crashes by individual severity level per year. So the crash prediction model for the basic freeway segments consisted of our SPF, which again, we use segment length as an offset. We included the AADT for the freeway segment, and then different adjustment factors based on the geometric and operational variables that we had available, and we'll summarize those in just a couple of slides here. For the speed change lane segments, we had the addition of the associated ramp ADT. So we didn't talk too much here about how we defined the different segments, but it was consistent with what's in the HSM. More details can be found there, but basically a speed change lane segment are those that were defined by the gore to the end of taper, which Ian had showed in the data collection section. And so then this includes the freeway as well as the ramp ADT and its interplay in the role of safety in those situations. Again, we attempted to identify adjustment factors that are consistent with the HSM. However, there were some areas where we weren't able to be consistent or may have missed out on some things that we would have all liked to have seen in the predictive method. In some cases, the data just weren't available. For example, we didn't have information on barrier offset or the clear zone width. If there were some cases where we had the same values for all sites. So in general, I think it was like 97% of our sites had 12-foot lane widths. So we really weren't able to establish a relationship between lane width and predicted safety in this case, just because we didn't have any variability. And then there were some cases where we had data, we tried to estimate the relationship, but the models based on the Ohio-specific data did not find a significant relationship. So in those cases, we couldn't include those in the model. So in terms of the overall SPFs that we developed for project design level, again, you can see that we have quite a bit of SPFs here. And we didn't find as strong a relationship with number of lanes that we see in the HSM, where it predicts it at 4, 6, 8, and I think 10 plus lanes for urban areas. What we tended to find was there was a split if there were 2 or fewer directional lanes. Again, we're talking directional SPFs in this case, or 3 or more lanes in one direction. So for the freeway segments, you can see again, we split by the crash type, whether it was multiple or single vehicle, the severity being fatal and injury or property damage only, whether it was a rural or urban segment, and then the number of lanes. For the entrance and exit speed change lanes, we estimated, again, consistent with the HSM, the crash types together. So multiple and single vehicle crash types were estimated together, but the severity levels were done separately. And in most cases, the rural and urban were combined. We didn't find significant differences. But for the entrance speed change lane property damage only, we were able to separate those out. So then in terms of our adjustment factors, you can see that we estimated the adjustment factors by the individual SPFs. And so we do have for freeway segments 4 different levels potentially for each of the adjustment factors. In some cases, adjustment factors only impacted multiple vehicle crashes or only single vehicle crashes, or have been more focused on fatal and injury or PDO crashes. So this table goes through, we did have about 10 to 12 different adjustment factors, such as inside and outside shoulder width, the width of a depressed median, the degree of curvature was available, so we included that in the models, the presence of median or outside barrier. Again, we didn't have information on barrier offset, so that was not included. We have an adjustment factor in here for the presence of an upstream or downstream exit, and then how the distance to that exit, as well as the ADT of the upstream or downstream exit or entrance. And then for the freeway segments, we did have the presence of a lane addition by ramp and a lane drop by ramp. And Kendra's going to go through some examples of those and how they differ from the upstream and entrances and exits. And then we also included an adjustment factor for multiple vehicle crashes if there was a type A or B weaving section present. We did not find any relationship with type C weaving sections. And then for the speed change lanes, we did find adjustment factors for left side ramps, as well as proportion of the segment that is curved in a couple of cases rather than the degree of curve. So then the final component here is the severity distribution functions. And so this table just provides an overview of which factors we found to impact crash severity within fatal and injury crashes significantly. So just as an example, for freeway segments and speed change lanes, higher posted speed limits were associated with more K and A level injuries, and as well as more B level injuries. And in this case, the impact was even higher for K and A. So basically, as speed goes up, severity goes up. And then kind of the opposite, as outside shoulder width goes up, or sorry, inside shoulder width goes up, we saw a decrease in Ks and As. So I'm going to go ahead and hand it over to Kendra to talk about the validation of those models.
Thanks, Scott. So yeah, get my screen set up here so you should be able to see that. So as a user of these SPFs here in Ohio, I'm excited to share what we've been working on and how it's going to affect us moving forward. So we've identified a cross-section of projects to use in the testing process, 26 total sites that were really diverse in nature, both urban and rural in context, and were either 2, 3, 4, or 5 lane segments. And as illustrated in this map here, we try to get a geographic diversity as well with our project samples. So we evaluated this with 4 predictive models: the uncalibrated HSM models, which were straight from the HSM, the Ohio calibrated SPF models, or HSM SPF models, and then the ODOT SPF models with HSM adjustment factors, but also the new SPFs with ODOT adjustment factors. So for the past several years, Ohio has been using calibration factors to adjust these SPFs and correlating HSM adjustment factors to account for Ohio-specific conditions. So the HSM models are bidirectional and analyzing both directions at the same time. So to simplify this process, what Ohio's done is they've modified the HSM formulas to essentially mirror the freeway segment and then divide the result by 2. But as Ian and Scott just detailed, these new SPFs are directional. And so that is specific to each direction, which will make this process much easier moving forward. So the predictive analysis results for each of these models were compared with the historical crash data from 2015 to 2019 when we could. So there were a few projects that because of construction activities, we had to use data from 2014 to 2018. So with the new edition of the Highway Safety Manual, these Part C crash modification factors, as they're called in the Highway Safety Manual, are going to be called adjustment factors. So that's what we've been talking about, these adjustment factors. So really want to get rid of the confusion with the Part D crash modification factors. So this table really illustrates the differences between the HSM adjustment factors and the new ODOT adjustment factors. So it's important to note that not all these factors are independently evaluated in the HSM, and I'll talk about that in a few slides, but also that we made some changes to these adjustment factors, even though they were included in the HSM, both HSM and the ODOT models. So for example, the median width adjustment factor differs between the HSM and the ODOT models. So in the HSM, this adjustment factor applies to the medians of all types. In the ODOT models, this factor is just applicable to depressed medians. So to evaluate these medians with the HSM methods, you'd have to get the proportion of segment with median barrier, the inside shoulder width, and the distance from the inside shoulder to the barrier face. In the new simpler ODOT model, only the proportion of the segment with median barrier and the overall median width is required for this analysis. So here's that new equation for the adjustment factor for the depressed median width. If the median is not depressed, the adjustment factor is just going to be equal to 1. For depressed medians greater than 60 feet wide, the adjustment factor will be less than 1, whereas depressed median widths less than 60 feet will have an adjustment factor greater than 1. So several of these adjustment factors aren't independently evaluated in the HSM. So for example, the HSM Chapter 18 lane changing adjustment factor simultaneously accounts for upstream entrances, downstream exits, lane adds by ramp, lane drops by ramp, and Type B weaving section presence, proportion, and length in both directions through one adjustment factor. So this factor can be really difficult to assess and follow when you're attempting to identify the individual effects of each of those components, or maybe when you're trying to quickly estimate the impacts of your geometric design decisions. So these new ODOT methods have a specific adjustment factor for each of these features: the downstream exit, upstream entrance, lane add by ramp, lane drop by ramp, and the weaving section. So we'll dig into those adjustment factors in the next couple slides here. So with the separation of these factors, we need to make a distinction as to when to use each of these lane changing adjustment factors. So the lane add or lane drop by ramp adjustment factor should be used only when the GOR is directly adjacent to the specific segment, like shown here in section 1. If the freeway segment is not bounded by the GOR, like in freeway segment 2, the upstream entrance lane change adjustment factor should be used. So the exit entrance ramp lane change adjustment factors are really similar. So for time purposes, I just want to touch on the exit lane change calculations. So both of these calculations require the proportion of the upstream or downstream lane changes within the segment. This equation only accounts for the proportion of the segment that is within a half a mile of the ramp GOR. So this implies that any piece of the segment outside of that half-mile threshold is not significantly impacted by the lane changing. So in the example of a 2-mile segment, the segment length within a half mile of the downstream exit is only 4/10 of a mile, assuming the speed change lane is 1/10 of a mile. The lane changing in the other 1.6 miles of the segment is insignificant. But conversely, if you have a 0.3-mile segment, all 0.3 miles of that segment are within that half-mile threshold for lane changing. So the only data needs for the lane addition by ramp and lane drop by ramp involve the ramp volume data. If a lane add or a lane drop is not present, then the adjustment factor is simply equal to 1. An important distinction to note with these ODOT models compared to the HSM models like Ian talked about is we now are able to implicitly account for type A weaving sections. Before they were indirectly evaluated by analyzing the short basic freeway segments and then using the entrance ramp data and adjustment factors with the upstream entrance and downstream exit lane changes. Type A weaving segments were never explicitly identified in that analysis. It was really only for type B. But it should be noted that the ODOT models don't really distinguish between a type A or a type B with the adjustment factor, just that it's a type, that it's present. So one of the completely new adjustment factors included in the ODOT models is the posted speed limit. This adjustment factor is just calculated by comparing the posted speed limit to the baseline speed for the character of the area, either urban or rural. And this is really a vast contrast from what's in the HSM, which don't implicitly account for speed in the analysis. So like Scott discussed, several factors couldn't be modeled. These are 5 examples of that are adjustment factors in the HSM that are not in these ODOT models, mostly because the data was not readily available, or like Scott said, with the lane widths, they were unable to determine the effect since 97% of the sites were the same. So once all of the 26 projects were evaluated using these 4 models, the results were compared to the historical crash data using 4 statistical features: the mean absolute deviation, the root mean square error, the mean absolute prediction error, and cure plots. So we could spend an entire presentation discussing these statistical values, but for the purposes of this, just know that these values account for the variability in the data as well as the relative accuracy of the results. So from the statistical analysis, 2 models really stood out: the Ohio calibrated HSM model, which we're currently using today, and the ODOT SPFs with the ODOT adjustment factors. These 2 models clearly outperformed the other model applications. And while not mentioned in detail here during the project-specific level evaluation, the one-directional SPFs almost universally outperformed the bidirectional SPFs. So the hybrid approach using the ODOT SPFs with HSM adjustment factors was found not to be a good approach, given that the data differences between the development of the safety performance functions between the HSM and the ODOT models. So looking at these 2 models in more detail, both have very similar measures of error, but overall the Ohio calibrated HSM models tended to underpredict crashes, whereas the ODOT SPFs with ODOT adjustment factors overpredicted crashes. The Ohio calibrated HSM model applies more variables and is thereby more sensitive to geometric factors, but with fewer variables, the ODOT SPFs with ODOT adjustment factors are easier to implement. And furthermore, the new ODOT models provide a better fit by severity level and for the basic freeway segments. So as we just discussed, these fewer data inputs are required for the ODOT model and then the HSM model. But the ODOT model requires about 14 inputs compared to the 17 for the HSM. But these models are inputs are simpler for the ODOT methods, usually just requiring that the analyst indicate if a feature is present rather than requiring specific measurements, which does make the analyst's life easier. So what's next and how is Ohio moving forward? It's been decided that we're going to go ahead and adopt the ODOT SPFs with the ODOT adjustment factors for the project level evaluations. Those that are in Ohio, that ODOT-specific HSM tool, the Economic Crash Analysis Tool, or ECAT, will be updated to reflect these new SPFs, the adjustment factors, and data inputs. If we want to further refine these models to better fit Ohio conditions, we would need to do more data collection, which would include horizontal curves, clear zones, barrier presence, and offset to travel lane, as well as volume information. But for now, we'll just use these new models as they were developed. And then the final report and fact sheet are published on the State Library webpage and our research website, and will soon be posted on TRID. And I believe we're posting the links to these documents found in the chat pod. And then updates to the ECAT will be coming soon with these new model calculations. So with that, we will take any questions that you might have.
Great, thanks, Kendra. I've been keeping an eye on the questions that have been coming in. I've responded to some of those, and we have a couple that I haven't yet responded to. Just kind of starting with the most recent that I've gotten. One of the questions we got was, were we able to identify the effect of the outside shoulder width on multi-vehicle crash frequency? So just looking at the slide 27 that we had presented earlier, we found a significant relationship with multi-vehicle fatal and injury crashes that does suggest as the outside shoulder width is wider, there are fewer multi-vehicle fatal and injury crashes. Unfortunately, we didn't find a significant relationship with any of the other crash outcomes. In general, the relationship was pushed toward negative, which means wider shoulder, fewer crashes, but the results for the other crash types weren't even close to significant. Another question that we had gotten was how many years of data were used for model development and which years? We had the 5 most recent years available. I want to say it was 2014 through 2018 crash data that were used to develop the models. I just got another one. How cure plots of the 2 selected types of models compare? Because of the level of specificity we were getting into in the SPFs, it's hard to compare them. As you'll note, the cure plot for the network screening SPFs were for total crashes and for fatal and injury crashes, while what we were looking at for the project design level SPFs were focused on individual crash types. And so we did get much narrower bands in the cure plots for the project design level. We did see improvement in the cure plots as we'd expect by including more information. Our predictions got closer, but it is hard to directly compare the two because of the level of specificity on those. And I think that is all the questions that we have so far. If there are any more questions, I think we do have 5 more minutes left. So one of the questions that just came in, did you consider developing directional models for network screening? We did not, and Derek Troyer could probably provide more information on their thoughts on this, but in general, because network screening models are a higher level and the data were already set up for bidirectional models, I'm guessing there really wasn't much. Well, I guess for a couple of reasons. So the results of this research for the network screening models are also intended to be incorporated into Safety Analyst. And so Safety Analyst does use bidirectional models. So I guess that kind of precluded the use of directional models. But in general, you probably can get into more refined details, but because of the size of the segments you're generally using for network screening, you probably wouldn't find too much of a difference for the directional versus bidirectional models. What vehicle and person level variables are in your SPF Ohio models? I'm trying to think. Basically, what we used from the crash data on this one was what you see with the difference in the SPFs. We didn't get into any person level information or vehicle level information specifically with the crashes. We just looked at whether there were multiple vehicles and the maximum severity of the crash, injury of the crash. And then I did get one more follow-up looking at the counterintuitive results for the number of freeway lanes. So we did drill into the details a little bit on where we were getting the counterintuitive results. So when we were developing the SPFs, again, we looked at multiple vehicles separate from single vehicle crashes, as well as the fatal and injury versus PDO. You'll see that in general, what we had found and was found on slide 26 was that there was a significant difference when we had 2 directional lanes versus 3 or more directional lanes. What we had seen from much larger data set that's included in the HSM was that there's an additional improvement of going from 4 to 6, 6 to 8, and 8 to 10 lanes. We didn't really find that. We saw the improvement of going from 2 lanes to 3 or more lanes in general, but because we're looking at separate SPFs for those, it's also not completely clear cut. In general, we may see an average reduction in some of those crash types, but what we saw was for some of the crash types, and I don't remember the details offhand, which is why I'm having difficulty drilling into those details. We did see that for most of the range of ADT, having more lanes may have resulted in fewer predicted crashes, but at a certain level of ADT, they kind of reach the same value or actually cross over. But I don't have the details offhand for which SPFs that we were specifically seeing those. So we got a question: how different is the identified hotspot ratio compared to the previous model with Ohio-specific model? I'm not sure if that has been addressed yet. We developed the SPFs, but I'm not sure if those have actually been implemented for hotspot identification to date. For the network screening models, did you develop cure plots using the same data used for the developing the models? In that case, yes, we used all of the data available. We did not withhold any data to develop the network screening SPFs, and so that's why we focused on using the cure plots as our primary method of validation, because we did use all of the data for developing the SPFs. And Derek just left me a note saying that they'll find out next month for the hotspots what the difference is with the new models versus the old models. And then we had one more question on, do you think with the data collected you could add any more to the PHV factor to account for varying degrees of operational conditions? So unfortunately, we did not have the level of detail necessary to account for the proportion of hours or proportion of volume occurring in high volume situations. We would have loved to incorporated that into the models, but we didn't get into looking at individual count stations as part of this to get at that level of detail for the network, because basically we had to either use data that were already existing in an ODOT database, or we would have had to have collected it, and we just didn't have the time available to go and collect a lot of that information for the project design level SPFs. Our main focus was on identifying the locations of gores and tapers so that we could separately look at the speed change lanes versus basic freeway segments. Then we got another question. Will you adjust by region district from the statewide model or use just one statewide model? So for the network screening, we did include the district level indicators. For the project design level, my guess is, answering for Derek, is that they'll use the same model for the statewide in that case. So then we got another question. Is there any general understanding as to whether the new models tend to be more conservative than calibrated HSM models? I wouldn't say that they tended to be more conservative. There were definitely some scenarios where they predicted higher or lower. I think just for the freeway segments, as Kendra's slide said, I think they tended to, I want to make sure I get this correct.
Yeah, the new models overpredict and the HSM calibrated underpredict.
Yeah, that's what I thought. Okay. Thanks, Kendra. And I think there's just one more question on how frequently does ODOT plan on updating the SPFs? Annually, every 3 years, or every 5 years? Again, I'd have to defer to Derek on that one. And I think that is all the questions that we received. Derek responded as needed and as time allows. Well, I see that we're at 2:03. I just wanted to thank everyone for your time today, and thanks for the really good questions. Hopefully I was able to answer as many of those as possible.